Hey everyone, in this video we're going to talk about section 5.2a, which is going to introduce the term logarithm. So this is something that we've been building up to for a while, and in your mathematical career you've been building up to it. You've probably heard a little bit about these, whether maybe you were in personal finance and heard about logarithms, or maybe you're studying for the ACT and you kind of came across a logarithm. Now's our time to learn it. So how we're going to get there is, it has to do with inverse operation. So we know that every operation has exactly one inverse or opposite operation. Okay, you've known about that since you started learning your math facts in elementary school. Well, remember the reason that we learn inverse operations is because they allow us to solve equations that use different operations. Okay, so the ultimate goal is to be able to solve. So for instance, let's say that an equation used the operation of addition. Well, if we want to solve for x, we're going to invoke that inverse operation, subtraction, to be able to do that. Okay, or if the equation has multiplication, we know that that inverse operation is division. Okay, or let's say that an equation was cubing something. Well, I'm going to use that cube root to undo the cubing. Okay, and all of that's fine and all of that's dandy, but the one operation that we really haven't been able to undo up until this point has been exponentiation. So if we have an exponential function, I want to get x, we don't really have a way to get the x out of the exponent, right? I don't have a way to undo the fact that the x, the x isn't the base, the x is the exponent, okay? So in the last section, we learned about exponential functions and their properties. So if we want to solve equations with exponential functions, we need a new inverse operation that's related to exponentiation. And that's going to be what a logarithm is. Now, from this point on in the video, I'm going to go ahead and splice this with a video that I made last year. So if the jump is a little bit weird, sorry about that. But so what's the inverse of an exponential function? So we've talked a little bit about how to find inverses before. We take our function, and then if we want to algebraically solve for it, we will swap our x and y. And then we can backwards solve from y from there. And this is where things get a little bit tricky, okay? So our y, or the variable that we're trying to solve for to find our inverse, is in the exponent. So right now in your mathematical career, I don't know if we know a lot of different options that we have to be able to get the y out of the exponent, okay? So when mathematicians a long time ago were presented with this option, they said, well, if we don't know an operation, let's make an operation, okay? And so in this case, their operation was inventing what a logarithm is, okay? So here's what our inverse ends up being. So our inverse, y, is going to be equal to log base b of x. Okay, so reading through what this says. So the log represents an exponent, okay? So these two things are the same. This exponent up here, y, is the same thing as this thing here, okay? So this operation is representing what that exponent ends up being. We were never able to fully get that y out of the exponent, so it's like we made a whole other, what do I want to say, expression to represent what that exponent will be, okay? A couple of things to notice here. So the b that we have here is our base, and then the x that we have here is what we call our argument, okay? And so that's what it was equal to, or that's what our original exponent, I guess, was. All right, that brings us to our logarithmic functions, okay? So those are the inverses of exponential functions. So the term log, or the operation log, is a mathematical operation that's going to be used to undo an exponent. So there's a few things I want to draw your attention to. First, our value of x must be greater than 0, okay? And so we're going to go off of that from this equivalent value of when we had switched that x and y, okay? Why does x always have to be greater than 0? Well, there's no value of y that I can plug in here that's ever going to give me a negative number, right? If you raise an exponent to anything, you either get a fraction or you end up getting like a positive whole number, right? So there's nothing that's ever going to make you get a negative number from here, okay? So that means here that whatever this value is in here, and we're going to call you that our argument, we'll go over that in a second though, that always has to be positive, okay? So you can't plug negative numbers into a logarithm. The second thing that we need to know is that b, and that represents the base of our exponential function, it must be greater than 0, but it also can't be equal to 1, okay? It can be any number you want. It can be a decimal, it can be pi, whatever you want, but it can't be 0. It has to be bigger than 0, and it has to be, it can't be 1. Let's think about why. Well, first, you're never going to see an exponential function like -3 to the x, okay? Our bases are always going to be positive numbers, okay? So it can't be negative. If it's 0, well, that doesn't make sense. And if it's 1, well, that's just the constant function 1. Okay, so you can really have any number as your base, just not any of those. Okay, converting between logarithmic and exponential form. So if we originally started with like our original y equals b to the x, okay, so that's our exponential function. Our inverse, or our logarithm, is going to be, is going to be x equals log base b of y. Okay, so a few things just to note from here. So from our original exponential function, the y is what it was equal to, and that's going to be what we call the argument of our logarithm. Okay, so that's our argument. Our base of our exponent is what we call the base of our logarithm. And then the x, which was the original exponent of our exponential function, is what our logarithm is equal to. Okay, so a logarithm, and I'm going to say this a million times, and I want you to say it a million times to yourself too. A logarithm is an exponent. Okay, it's representing an exponent. Okay. We have a couple different types of logs. Okay, so the first one's called a common log, and so a common log is going to be when our logarithm has a base of 10. Okay, so whenever you see a log base 10 of x, since it's so common, we also just call that, and more commonly write this as just log of x. Okay, the second type of log that we're going to see a lot come up is called the natural log, and that's going to use Euler's number e as our base. Okay, so a couple things with Euler's number e. It is an irrational number. And it's approximately equal to 2.71828. It was first kind of identified and made popular by Leonhard Euler. Okay, it looks like Euler. It's called Euler. And in Calc BC next year, if you hang around long enough, we will prove why this is true. But this number comes up really from kind of financial stuff. We can get it by evaluating the limit as of 1 plus 1 over x raised to the x power. We're going to evaluate that as x approaches infinity. Okay, that's equal to e. But we'll get there. I won't get too far ahead of ourselves. Okay, so the natural log is when our logarithm has a base of e, log base e of x. Okay, and more commonly, we're going to see this as ln of x. Okay, it stands for natural log, but we should know that the base there is e. So, looking at our next couple of examples, we're going to write the following in either exponential or logarithmic form. So we need to be able to go back and forth between logarithmic form and exponential form. So the first one that we have, I see that we have a exponential form. We're going to write it as a logarithm. So first I'm going to start this off as log. Now our base of our exponential was 2, so the base of my log is going to be 2. Okay, what it was equal to was 8, so that's going to be my argument. And then I know a logarithm is equal to an exponent, so I'm going to set it equal to what the exponent of this exponential form was. So its equivalent form is log base 2 of 8 is equal to 3. Okay, next one is also in exponential form, so we have e to the 10 is equal to x. I'm going to circle this. Excuse me. Okay, so we're going to have log base e. What it's equal to is x, and then its exponent is 10. Now, I see that I have a log base e, so really the way that we're going to write this is natural log of x is equal to 10. Okay, after this, you're going to see me more just commonly jump to the natural log from there. I'm not going to write it as the log base e, but just to know, that's really what it is. Okay, again, we have another exponential form, so I'm going to write it in its logarithmic form. So I'm going to have log base 10, what it's equal to is 100, and then a logarithm is an exponent, so it's going to be equal to the exponent here. Now, I see that I have a log base 10. I'm going to write that as the common logarithm, so log of 100 is equal to 2. Okay, the next few that we're going to look at are going from logarithmic form to exponential form. So starting off here, I'm going to evaluate, or I'm going to figure out what my base was. In this case, my base was e. So that'll be the base of my exponent. What it's equal to is 9, because a logarithm is an exponent. And then the argument of this was x plus 2. So I'm going to write this as e to the 9 is equal to x plus 2. And I know you're probably itching to be able to actually solve that from there. That's not what this is about. We're just rewriting the form. Okay, next one that we have is the natural log of 5x plus 1 is equal to 6. Well, I know that the natural log is really log base e, so I know that the base of my exponential is going to be e. What it's equal to is 6, so that's my exponent. That's equal to 5x plus 1. Okay, last one that we have log of 100 is equal to x. I see that this logarithm doesn't have a base, so I know that this is the common log, so it really has a base of 10. So I'm going to have 10, what it's equal to is x, so that's my exponent, and then the argument was 100. So 10 to the x is equal to 100. And again, you're probably itching to be able to solve that. Just stop. We'll have plenty of time to do that later. Okay, so being able to rewrite the two forms are going to be really important. Next thing that we're going to be able to do is evaluate the following without a calculator, okay? So the cool thing about this is if everything kind of aligns correctly, we should be able to not use a calculator. Now, sometimes you do have to, but not in these. Okay, so we have log base 2 of 16, and we want to know what it's equal to. So I'm going to say that's equal to question mark. So to be able to evaluate this, I'm going to turn this into exponential form, okay? So I know that exponential form, 2 is my base. I'm not really sure what my exponent is, but I know that this is going to be equal to 16. So I'm trying to think, okay, what number do I need to raise 2 to get me to 16? Well, 2 times 2 is 4, times 2 is 8, times another 2 is 16. So this is equal to, why did I write it that way? This logarithm is equal to 4. Okay, our next one that we have log base 7 of 1 over the 5th root of 49. Okay, it might be a little bit easier for us to undo this so we don't have everything going on in the denominator. So I'm going to rewrite this as log base 7 of, okay, so that's going to be 49. It's in the denominator and it's a 5th root. So to the negative 1/5 power. All right, okay, so it's like I want to know what this is equal to. Well, let's put it in its exponential form. So I'm going to have 7 to some sort of power is equal to 49 to the negative 1/5 power. Okay, from here, it would be really helpful if we could figure out what the base needs to be, right? So like here, it was easy to tell, okay, 7 times 7, or 2 times 2 times 2 was equal to 16. Here, I'm going to say, let's try to get our bases to be the same so we can see what our exponents need to be. Okay, so how can I rewrite maybe 49 as a base of 7? Well, I could rewrite this as 7 squared, right? Because that's 49. And that's being raised to the 1/5 power. Well, okay, I have two powers, a power being raised to a power, so this is equal to 7 to the negative 2/5 power, because I'm going to multiply those. So what's that to say? So that's to say 7 to some sort of power has to be equal to 7 to the negative 2/5 power. And since our bases are the same, I know that this is going to be equal to negative 2/5. All right, let's keep going. So we're going to have log of 0.00000. How many zeros? 1, 2, 3, 4, 5. 5 zeros, okay? I want to know what this is equal to. So first, let's go ahead and rewrite this a little bit. Since this is the common log, I know my base is 10. So 10 to some sort of power is equal to 0.1, 2, 3, 4, 5. Okay, well, it might be helpful if we had that written maybe as, it's a decimal, maybe writing it as a fraction would help. I think that's 1 over, tell me if you think I'm wrong, that's 1 over 100,000. Okay, so maybe let's rewrite this again so they have the same base. So we're going to have 1 over, well, what do I need to raise 10 to get me to 10,000? well, 10 times 10 is 100, times 3 is 1,000, 1,000 times another 10 is going to give me 10,000, times another 10 is going to give me 100,000. Yeah, 10 times 10 is 100, times 10 is 1,000, another 10, yep, okay, so that's 10 to the 1, 2, 3, 4, 5, fifth power. So that's going to be 10 to the negative fifth power, and so in this case, I see that my exponent has to be negative 5. Okay, again, we have another common log, so in this case, I have, it's equal to some sort of thing, so I have 10 to some sort of power is equal to the fifth root of 1, 2, 3, 4, 10,000. Okay, so let's rewrite them so they have the same base. So I could write this as 10 is equal to, okay, so 10,000 I think we decided was going to be 4, 10 to the fourth, and then this is raised to the 1/5 power. If I go ahead and multiply those powers, I'm going to have 10 to the 4/5 power. So my exponent needs to be 4/5. All right. Looking at our next one, we have the natural log of e to the third power. So, rewriting this, I know, well, from here, this is really log base e, okay? So I have I have e raised to the question mark, and it's going to be equal to e to the third. Well, that was pretty easy. We didn't have to do a lot of manipulation. I know that this is going to just be equal to 3. So hey, that's kind of cool. One thing maybe to notice here, if the base of our logarithm and part of the argument are the same, then it's just equal to that exponent of the argument. Let's see if the next one holds true. So we have the natural log of the square root of e. Okay, so I'm going to rewrite this. That's the natural log of e to the 1/2. Okay, and I want to know what that's equal to. Well, I know that the natural log is really log base e, so if I could rewrite this, this would be e to the question mark is equal to, okay, what our argument is, which is e to the 1/2. So in this case, it does hold true. This is going to be equal to 1/2. All right, the last two that we have are already in exponential form. We're going to rewrite those so they are in logarithmic form. So I want to know what this is equal to. Okay, so we have to put it in a logarithm form. So the base of our logarithm is 8. Okay, the argument is going to be our question mark. And then what it's equal to is the exponent. So log base 8 of 5. So what does our question mark need to be so that these two are equivalent? Well, it has to be 5. All right, and the last one that we have here, we have e to the natural log power is equal to 12. So again, let's go ahead and rewrite this in logarithm form. So the base of our logarithm is e, okay? The argument that we have is question mark, that's what we're trying to figure out, and I want this to be equal to our exponent, natural log of 12. So again, remember log base e is really the natural log, so I'm going to rewrite this as natural log of something is equal to the natural log of 12. And for these two statements to be equivalent, I know what needs to be in that parentheses is 12. All right, the last few that we have, we're going to use a calculator to evaluate the following, and they're going to round to the nearest thousandth. Okay, so remember 3 decimal places. Now, everyone has different calculators, so go ahead and grab those out, and you should go ahead and look for the logarithm button within your calculator. Okay, we're going to go ahead and just practice evaluating these and typing them in. So I'll go ahead, pause, give you a second. When you're ready, we'll go ahead and check our answers. Okay, so the first one we have log of 16.427. This should be equal to 1.216. The next one's going to be the natural log of 23.221. 3.145 should be our answer. And then the last one is log of negative 2.457. In this case, your calculator should have given you an error message. This is going to be undefined or does not exist. Okay, and either one's fine to write. Okay, and you're probably thinking to yourself, okay, why is that undefined? Why does that not exist? Well, let's go ahead and rewrite this in exponential form to figure out why. Okay, so in this case, our base is 10. So 10 to something is going to be equal to negative 2.457. Remember what we were talking about a little bit earlier? There's really nothing that we can, there's no exponent that I can have that I raised 10 to that power that's going to give me a negative number. Because if I make this a negative number, well, that just goes ahead and moves it to the denominator, but it's still positive. If it's 0, it's just 1. And if it's a positive number, it just makes it a bigger positive number. Okay, so we're never going to end up with a negative out of our exponent, so that means that our argument of our logarithm can never be negative. So let's go ahead and we'll summarize that. Okay, so I said we cannot have a negative argument in our logarithm, and the reason is our exponent will never make a negative number. All right, we're going to go ahead and pause our video here right now. I will see you all later.